So after discussing about an orthogonal tensor's principal vector and principal values, let's talk about what an orthogonal tensor does to the relative orientation of any two given vectors. So let's put down two vectors. Okay, so here are two vectors A. So here is a vector A and a B, and the angle between them is theta, and we are operating on these two vectors by the tensor Q, which is orthogonal. The first fact is that the dot product of the initial two vectors is same as the dot product of the final two vectors. What does this mean? Well, remember A dot B is A B cosine theta. Okay. Well, what we and then QA dot QB therefore must be QA QB cosine whatever is the new angle between them, let's call it phi, but we know that QA and A are the same. Well, that's the basic property of orthogonal tensors, so that this becomes A B cosine phi. This equality says therefore that cosine theta and cosine phi must be the same. So what does that mean geometrically? It means, well, let Q take A to some other orientation, let's call that A. Because theta and phi are the same according to this, what it means is that if I was to draw a cone, let's say, yeah. So here is a, okay, so let's give this some other. Okay. So vector B can be let's see if I get this right. I'm struggling with the drawing a bit. I think maybe I should, because B is larger, I'll put the over here. That's easy, better. Okay, so this is not QA, it is not A, it is Q dot A, and this is Q dot B, and this angle is phi equal to theta. So what we are saying is that when Q operates on this pair A and B, the only thing that can happen is that A and B are now located so that wherever QA is, QB will be on a cone around it, and the cone angle will be also be theta. That's a very important property. So the relative orientation, so what we are saying is that Q preserves the relative orientation of A and B. Okay, great. So that's the first property. The second property is I will need to add a page here. Let's see, where am I? I'm over here. Add page. Okay. So the second property that I have is that the plane normal to the principal vector E3 is invariant under Q. What does that mean? Let's first draw the invariant vector. So I'm going to draw it over here. So let's say this is the invariant vector E3, so that the plane normal to it is this. Okay. And in that plane, let us take a vector. Let's call that vector A. Okay. Now this angle must be 90 degrees. What we have just learnt is that when Q operates on this, we must get back. Let me just copy and paste the image again. So So when Q operates on E3 and A, what will happen? Well, we know that Q dot E3 is lambda 3 E3, which is plus or minus 1 E3. So therefore, what's going to happen then is that either we will, when Q operates, either we will get plus E3, E3 will become either plus E3 or minus E3. What does that mean? That means, let's kind of make this a little better. So what's going to happen then is that so I can get back either minus E3 or I can get back E3. That is okay. Whatever it is, the output of Q will either be E3 or minus E3. What will happen to Q? What will happen to Q dot A? Well, we have just learned that the angle between A and E3, the relative orientation must be preserved. That means Q dot A must be normal to plus E3 or minus E3, which means that Q dot A must be in the plane somewhere, right? It must remain on this plane. Q dot A must remain on this plane because this angle must remain 90 degrees. Okay, so therefore this plane is called the invariant plane. Okay, any vector, okay, any vector in this plane will remain in it under the operation of Q. Okay, hence called the invariant plane. So we now ask ourselves, what are the consequences of the normal plane to E3 being invariant under Q? The consequence is that we now realize that the orthogonal tensor Q will either rotate objects about E3 or reflect them appropriately about the invariant plane. So what do I mean by that? Let's understand that by the picture over here. Okay, this picture. So over here I have a vector A, and what I have done is that I have simply split the vector A into a component in the invariant plane and a component along the principal vector E3. So we can write down that A is A3 E3 plus A perp, and this A perp lies inside the invariant plane. And we ask ourselves the question, what happens to A when Q operates on it? Well, let's just write down some equations and see what we get. So we get Q operates on A, which is simply Q operating on A3 E3 plus A perp, okay, which will give me, well, what is, let's remind ourselves that Q dot E3 is lambda 3 E3, which is either plus or minus E3. So this will be plus or minus A3 E3 plus Q dot A perp. Okay, both these quantities, this is in the invariant plane and this will also be in the invariant plane, because we have just said that any vector which is on this invariant plane remains in the invariant plane. We also know that Q, the basic property over here, that this must be the same, that the length of the A perp vector remains the same. So what will happen really is that this vector A perp will simply swing into some other direction while remaining in the plane. Okay, but this A3E3 will either become plus A3E3 or minus A3E3. So either it will remain this or it will flip in the opposite direction. Okay, depending on whether lambda 3 is plus 1 or minus 1. So what we have is basically this picture, which I have already drawn for you because I didn't want to waste your time while I struggle with drawing. Okay, so let me first eliminate the right side of the picture so that you don't get confused by the clutter. Okay, all right. So here I am operating with Q on this picture, the one you saw over here, and lambda 3 is plus 1. When I do that, as I said, A perp simply swings over to this one, to some QA perp where the lengths are the same, and let's write this down. A3E3 remains the same. That's what we said over here if lambda 3 is plus 1. So therefore, this vector A produces QA, which appears to be a rotation about E3. Okay, so this is, so let's write this down. This is rotation about E3, right? So this is lambda 3 equal to plus 1 case. Okay, what happens when lambda 3 is minus 1? Well, we already know the answer. Nothing changes for QA perp, it swings as before, but A3 E3, the E3 component of A becomes minus, it flips over. Okay, so the picture was this. Let me change some of this clutter. Okay, all right. So now A perp again goes to QA perp just like it did over here, but A3 E3, which remained unchanged, flips over, and I get this is minus A3 E3. So therefore, this vector A is reflected about the invariant plane, is reflected about this plane. Okay, not over like this, but across the origin, across the kind of the point at which it emanates from. Okay, so this is what I am calling is reflection about the invariant plane. Okay, all right. So that's what I have. Okay, all right. Now let me, so this was about what happens to vectors. What about, but here I have written objects. What about an object? Okay, so let's consider this picture over here. I have here a box, right? And the box is a parallelogram and the parallelepiped, and the parallelepiped axes are given by A, B and C, and C is along E3, and the question is what happens to this again when Q operates on it. What do you get? Again we will split it into two choices, when lambda 3 is plus 1 or lambda 3 is minus 1, and the answer will be given by this picture. So if I have lambda 3 is plus 1, then, well, we know from here that the relative orientation of A and B can't change. So A and B simply swing and become QA and QB, and this angle remains theta. Okay. However, something can happen to C depending on lambda 3, but lambda 3 is plus 1, so C remains C. and you get back this object, which again looks like a rotation around E3. Okay, so rotation of the box about E3 when lambda 3 is plus 1. When lambda 3 is minus 1, nothing changes for QA and QB. They remain like that. So this one is QA, and this angle remains theta. Okay. However, C now flips and you get QC is minus C, so that the box which remained on top of the plane of the invariant plane now is below the invariant plane. So the box has rotated and then been reflected about the invariant plane. Reflection about the invariant plane. So we really understand an orthogonal tensor. It either rotates objects or reflects them. Okay, great. Here's one more identity which I will leave you to show. It simply says that if I have two vectors A and B, so that C is A cross B, and the question is what happens to this when Q operates, and this identity is showing you that Q A cross Q B, well, this is really lambda 3 times C. Okay, because A cross B is C. Okay, I will leave this for you to prove. Okay, finally the determinant of an orthogonal tensor. We have seen earlier that the determinant let me actually insert a new page here, add page. Okay, let me also go to single page now. So what we have over here is we know that the determinant of any tensor is the product of the eigenvalues. Well, in this case the eigenvalues are lambda 1, 2 are complex conjugates and lambda 3 is plus minus 1. So you simply multiply them and you will get that the determinant of Q is lambda 3. So it is either plus 1 or minus 1. The consequence is that, as I will show you, that if the determinant is minus 1, if lambda 3 is minus 1, then volumes get inverted. That can be easily shown. So let's take three vectors, any three vectors, and define a so these three vectors will define a parallelogram, a parallelepiped, right? So I'm trying to draw this and I'm going to struggle with it. Okay, so that's my parallelepiped. Let's try again to make it a little better. Okay. So the volume is C dot A cross B. Okay, I think that's right. Yeah, let's assume it's right. So now the question is, what happens to it when Q operates on it? Well, I will get three vectors QC, QA and QB, and the question is, what is the new volume? So the new volume will be QC dot QA cross QB, and by using these identities, QA cross QB is lambda 3 times, so let's use that one. So this will become Q dot C times lambda 3 q dot a cross b, and this one you can bring q over to this side by using this formula, which I think you have done, that a dot b is a transpose dot a dot b. So I will use that formula over here to bring q over here. It becomes q transpose. Q transpose times q will be identity from here, and identity times c will be c, and I will simply get that this thing is c is lambda 3 c a cross b, which is lambda 3 times old volume. Okay, so if lambda 3 is minus, then the volume is inverted. Okay, this is actually similar to what happened over here. When lambda 3 was minus, the box was reflected. When lambda 3 was plus, the box remained on top of the plane. Okay, so you didn't have to kind of invert the box through itself, but when lambda 3 is minus 1, you had to push the box through itself to get the final answer. And this pushing through the box through itself is inversion, and the volume becomes negative. So that's all about the orthogonal tensor, and now we'll move on to the tensor which is going to be crucial in dynamics, the rotation tensor.